Alright, silly people, here's the situation. We're doing some proofs on some wave functions to just kind of stipulate on some basic properties of wave functions. Um, the first one is that in a given um, time-dependent wave function, that if it satisfies the time-dependent Schrodinger equation, that the energy E has to be real, um, which is cool. So I'm going to present a proof by contradiction, um, assuming that E is real. You can write the form of a little time-dependent waveform as E naught plus I gamma times T over H bar. Right now, E is complex. We're going to prove that it can't be. So what you want to do is you want to be like, okay, basic property of wave functions is that if you take the integral over all space of the modulus squared of it, then you should be getting 1 every time. So let's do that. So we have psi star psi, and we have the complex conjugate first, which is going to be I E naught minus I gamma times T over H bar, and we have minus I E naught minus I gamma T over H bar. That's the modulus squared, which should be equal to 1.
Be careful, silly people. When I wrote that second exponent in the integral, it was supposed to be a positive sign on the I gamma because it's just the non-complex conjugate version of the wave function. So it should be minus I times E naught plus I gamma. And then the math that follows reflects that. So make sure to write your plus sign.
So multiplying that I through on each exponent, you have an I E naught, you have a minus I squared, which is just 1 gamma times T over H bar. And then on the other one you have minus I E naught. Again, minus I squared is just positive, both multiplied by T for H bar. So when you multiply those together, the terms which depend on E naught will go away, and you're just going to left with 2 gamma T over H bars. What's cool about that is none of that depends on space. So you can yank it right out of the integral. Psi star psi dx equals 1. And then assuming that the wave function psi, the time-independent wave function, will conform to the time-independent Schrodinger equation, then this thing is equal to 1 by itself, which means you better find that the exponent of 2 gamma t over h bar is equal to 1, which means that you better find gamma is equal to 0. So all of that just goes to show you that the energy cannot take a complex form for time-dependent wave functions. Um, Next bit, it's asking if um, if a wave. So okay, wave functions that satisfy the time-independent um, Schrodinger equation have to be real. Um, and even if they aren't real, then you can represent them using a linear combination of real and complex wave functions. What do I mean by that? So I'm gonna write the time independent wave function as minus h bar squared over 2m d squared over dx squared of psi, time independent wave function, um, plus v psi is equal to e psi. If you take the complex conjugate of that entire equation, then you get the same thing. It's just with some stars on the sides. Um, so both of these, like the wave function, the complex conjugate of the wave function, both satisfy the Schrodinger equation, which doesn't imply that the wave function is always real, but it does mean that if we pick some arbitrary real time-independent wave function, which I'm going to call psi1, um, which is real, then you can also have a linear combination of it with its complex conjugate, which is also going to end up being real and satisfies the Schrodinger equation. Right. Um, just because whenever you take like any linear combination of wave functions that necessarily satisfy the Schrodinger equation will also satisfy the Schrodinger equation. You can also introduce a psi2, which is complex, and have a c times, or so it's I times c psi 2 minus d psi 2 star is also a real linear combination of that wave function, um, and also will satisfy the Schrodinger equation, which means if you have a complex wave function psi 2 and you want to represent it as a real wave function, you can always do that, because now you can say that the linear combination a psi 1 plus b psi 1 star plus I times c psi 2 minus d psi 2 star, um, which is again a real combination and satisfies the Schrodinger equation. So you can take any complex time-independent wave function and turn it into a real one, um, just by finding something else that solves for the Schrodinger equation. Okay. The next proof is just kind of asking, what if what if the potential function in your Schrodinger equation is even? Um, and what does that mean for the wave function itself? Well, let's write two different versions of the Schrodinger equation, one where we're evaluating at positive x, so v of x psi of x is equal to e psi of x, and then one where we're evaluating it minus x plus v minus x psi minus x is equal to e psi minus x. Okay. Those two should independently satisfy the Schrodinger equation by themselves. The interesting thing is, since we know that the potential is even, we can rewrite the second one with Vx in place. Right. The interesting thing about that is that it means that we can say that the wave function can be either even or odd, right? Um, even if psi of negative x is not equal to psi of x, which would mean it is odd, then the wave function still works. It's still the same thing. And therefore, you can make wave functions that are linear combination of even and odd wave functions. So you can have one like a psi e, which is an even, and a psi o, which is odd, and you can make a linear combination of them like psi e plus or minus psi o that will also be either even or odd. And also satisfies the Schrodinger equation. So just some general statements about wave functions in this one.